All right, thanks for being here on time. I think we've got a few people who are late, so I hope they're not too disruptive. I was just watching the last video before class and again noticing how noisy the seats sometimes are, so do your best to stay as still as you can, although I'm sure there's some movement and that can be okay. Just do your very best. Here's the outline of the class today. So lecture A, we'll do another example with the central limit theorem. That's going to be our most important kind of calculation, by the way. This calculation is using the central limit theorem. Addition rule for disjoint events. Disjoint events are also called mutually exclusive events. Our book calls them disjoint. Venn diagram, that's something new. General addition rule, conditional probability. And then in lecture B, multiplication rule for independent events, general multiplication rule, and an introduction to something called binomial random variables, which are very common and useful. Quiz today is going to include some things about the multiplication rule for independent events. I did talk about it in lecture B last class, so it is technically something that is fair game. So realize that I'm probably not going to get into it in lecture A today, but it's something that we did talk about last time. Also, starting with the quiz that comes this Thursday in 2 days here, I think the quizzes are going to get a little harder. I mean, the homework's going to get harder as well as the quizzes. The quizzes are going to be less factually based and more problem-solving based. I mean, there'll still be facts to know, but there will be 1 or 2 problems, typically most quizzes, where you'll actually have to do a little problem solving, probably starting with the next quiz on Thursday. That tends to be a little tough. Okay? The math content goes up in difficulty, and the quizzes are going to be tougher too. So again, if you haven't been working hard to this point, if you've sort of been cruising along and doing okay, it gets harder, and so you're really going to want to bear down and work harder. So let's start with an example of the central limit theorem. Again, here's the statement of it saying something. The key thing is this is about the sampling distribution of x bar, the sample mean. Okay? The sampling distribution, this idealized histogram, if you will, though it's really a density curve, that reflects probabilities related to the sample mean and what you can expect in repeated random sampling. In real life, you typically only do 1 random sample when you're actually doing some statistics. These probabilities only have meaning in repeated random sampling, but we still can interpret what they mean with specific samples. And we can interpret things ahead of time as far as expectations go. Here's an example. One big application of statistics to business is the insurance industry. What is insurance? You've probably heard of insurance before. The idea of insurance is that we all face risks that are unlikely but carry a high cost, like a fire destroying your house. So what do? To deal with those risks, you form a group of people who share the risk. And you all pay a relatively small amount, relatively speaking, it could still be large for your budget, called a premium. And the insurance policy, the company, pays a large amount in benefit to those few people whose houses burn down. So an insurance company, how do they make money? They look at past data, they look at records for homeowners and see that there's a certain mean loss from fire based on past data and a certain standard deviation. And we're going ahead and pretending in this problem that on average, if you average all the losses over all the homes in the whole country, say, that the average loss is $250 per house. Now, plenty of houses are not going to get on fire, and so their losses from fire is going to be 0. But then there are going to be some houses that are on fire and maybe burned down completely, and their losses are going to be in the hundreds of thousands of dollars. So that mean and that standard deviation is with respect to that kind of distribution, which would be very strongly right skewed. And they're very high at 0, actually. Lots of people would not have any fire damage. The company plans to sell fire insurance for $250 plus enough to cover its costs and to make a profit, right? They're not going to be in business if they can't make a profit. So, but we're going to focus on the 250 here. They do want to make a profit, though. Part A, why would it be unwise to sell only 12 policies? And why is selling thousands of policies a safe business? And part B, we want to get more precise. If the company sells 10,000 policies, what is the approximate probability that the average loss in a year for those 10,000 policies will be greater than $275? All right, so intuitively, why is it unwise to sell them 12 policies, for example, or 10 or 20? Why would that be an unwise thing to do? Think practically, think common sense. What if there's one fire in that group of 12? They're going to lose a lot of money. I mean, most likely there wouldn't be any fires in 12 houses. So most likely they'd make 250 times 12, plus more to cover their costs and make a profit, although that's taking into account the possibility of loss initially. But if even one house went on fire, they might have to pay out $250,000 and they'd lose money. They'd lose almost $250,000. On the other hand, if they sell to thousands of people, thousands of homeowners, say 10,000, if they sell those policies for $250 each, then they're going to take in $2.5 million. If a few houses burn down, they might lose, say, 500,000 of that and still make a lot of money. But again, they have to cover their costs and make a profit. Okay? So that's the basic idea. You don't want to sell to just a few people. You might make money, you might even say you're likely to make money, but if even one person loses a house, then you're definitely hurting. Whereas if you sell to a lot of people, then you make a lot of money and still only a few houses burn down in this case, so you still make money. Spread that risk over a lot of people. Part B is a more precise computation related to the central limit theorem. Specifically, we're saying we sell 10,000 policies. What is the approximate probability that the average loss in the year will be greater than $275? So it's a probability calculation. Use probability notation as we've been doing. Okay? Again, I want you to use this notation. And tell the graders to be picky about it. Use it and use it right. Probability of something, you use parentheses here. That entire expression represents the answer. The number, that's the probability. What goes inside the parentheses is a description, oftentimes, of what the event is. In this case, the probability you're thinking about is the event that the average loss, or mean loss, will be greater than $275. X bar is the mean. What's the probability that X bar is bigger than 275? All right? X bar is the sample mean. Sample size is 10,000 here. 10,000 policies. What's the mean loss based on previous year's data is $250 per house technically. And what's the standard deviation? Looking up there, that's $1,000 per house. You've got to use this information, all three pieces of information here. Because of the central limit theorem, that's a pretty large sample size there. We know X bar has a sampling distribution that's approximately normal. Before I try to solve this problem notationally, let's try to estimate the answer graphically. Let's imagine drawing the sampling distribution of X bar. Because of doing simple random sampling, that's what you imagine when you're thinking about selling 10,000 policies. It's not really a random sample, but you can sort of imagine you've sold 10,000 policies to 10,000 random homeowners. Because it's unbiased, this should be centered on the population mean. Mu is, what was it, 250. Mu sub X bar, that's the symbol that represents the mean of the sampling distribution of X bar. Mu without an X bar, that's the population mean. When you do simple random sampling, these two things are equal. It doesn't work that way for the standard deviation, but for the means, they are equal. It's at 250. What about the amount of spread as measured by the standard deviation of the sampling distribution? What is that distance right there? We've called that sigma sub X bar. It's not equal to sigma, but it's related. It's sigma divided by square root of n. In this case, that's $1,000 divided by square root of 10,000, square root of n. Square root of 10,000 is 100. $1,000 divided by 100 is $10. That's the standard deviation of the sampling distribution. We're wondering again, what's the approximate probability that x bar is going to be bigger than 275? 250 again is right here. This distance right there is 10. This has got to be 260. Go 10 more to the right, it's got to be at 270. Go 5 more to the right, it's at 275. The chance of x bar being greater than 275 is the area under this curve to the right of 275, which is pretty small. You should expect a small answer. This is such a good thing to do, okay? Rewatch the video here to listen to what I said. It'd be a very good idea. We're going to be doing this kind of drawing and thinking over and over and over again through pretty much the rest of the course. You got to get this right. This tells us to expect a small answer. In fact, you can even predict what z is going to be pretty easily. That's 1 standard deviation above the mean. Here's 2 standard deviations above the mean. That's 2.5 standard deviations above the mean. Z is going to be 2.5. Convert to z. Again, it feels like the x bar magically turns into a z. It's not magic. It's just a definition, essentially. And the fact that the central limit theorem says that x bar is approximately normal. So when I let z equal x minus mu over sigma, or in this case, x bar minus mu over sigma, then it is a standard normal variable. 275 minus 250, not divided by 1,000. Don't divide by 1,000, divide by 10. Divide by sigma over square root of n. You could write it initially in here as 10,000 divided by 1,000 divided by square root of 10,000. It's a 10. That's the most common mistake here. That's 25 up top. This is the probability of z being greater than 2.5. Go to table A. I always pressed the wrong thing. Take 1 minus this number, or because of symmetry, I hope you realize you can also look at the negative 2.5. 1 minus that number is going to be this number, 0.0062. Maybe for extra emphasis, I'll still write it as 1 minus. 1 minus 0.9938, you can look in your book to confirm that, is 0.0062. 0.6% chance. Less than 1 out of every 100 years. In less than 1 out of every 100 years would you expect the mean losses to be greater than 275 if this really is a reflection of the population. Now, that's really at the current time. I mean, 10, 20, 30 years in the future, house prices are going to go higher, and therefore losses are higher to fire. So this is really only valid in a short term. But that's the idea. It would be pretty unexpected to get sample mean losses than 275. And the point of that is that you're pretty safe setting your premium to be 275 or higher, at least if you want to cover your losses. You get that's the main moral. You get a small chance that the losses are going to be 275 per house or higher. So you're pretty safe if you're ignoring expenses and profit. You're pretty safe setting your premium at 275 to cover your losses, your expected losses. That's the application. Okay? So again, we're going to be doing calculations like this over and over again. Any questions at all? Can I clarify anything? Please stop me. So we've gone over these basic probabilities rules last time. We're going to focus on this one at the moment. This is called the addition rule for disjoint events. P of A or B is the sum, P of A plus P of B. The probability of A or B occurring is the probability that A occurs plus the probability that B occurs. When A and B are disjoint, which means they have no outcomes in common, which means they can never occur simultaneously. Doesn't mean they are complements, it doesn't mean they're opposites, it means they can't occur at the same time. For example, if I flip a coin 4 times, the event that I get 1 head and the event that I get 3 heads are disjoint. If I get 1 heads, I didn't get 3 heads. If I get 3 heads, I didn't get 1 head. They're not complements because you could also get 2 heads or 4 heads or 0 heads. But they are disjoint. That's also called mutually exclusive. And use that in the last assignment. And you should continue to know it to be able to use it. We're going to use a more general form here in a minute called the generalized addition rule. But I also want you to know that we're going to draw diagrams called Venn diagrams that are going to be helpful for us as a problem-solving tool to understand intuitively the idea behind the formulas, especially. And here are different regions that you can make with the Venn diagram. And thinking about 2 particular events, A and B. What you want to imagine when you see this picture is you want to imagine the box as representing the entire sample space, the collection of everything that can happen. And you want to imagine A and B to be particular events. So for example, with flipping the coin 4 times, A could be the event that I get, well, if there's some overlap, A could be the event that I get an even number of heads. And B could be the event that I get 2 or more heads in 4 flips. There would be some overlap between those events because if I get 2 heads or if I get 4 heads, that would both be even and be 2 or more. Okay? Maybe you want to write that down. Flip a coin 4 times. That's hard to see over there, isn't it? 4 times. If A is the event that I get an even number of heads, and B is the event that I get greater than or equal to 2 heads. Can you see that? Flip a coin 4 times. This marker's not working so well today. Flip a coin 4 times. A is the event that you get an even number of heads, meaning 0, 2, or 4 heads. And B is the event that you get 2 or more heads, meaning 2, 3, or 4 heads. These do have overlap. There would be overlap between these events. They could occur at the same time. They're not disjoint. Because if you get 2 heads or if you get 4 heads, that satisfies both conditions. The intersection, so to speak, which is this region right here, that's common to both of them, would be when you get 2 heads and 4 heads. One of those 2 or 4 heads. Okay, so these are these shadings here are different regions that you could be thinking about. What's shaded here represents all of B. What's shaded here represents being an A or B, one or the other or both. Getting even number of heads, getting greater than or equal to 2 heads, or both. This represents A. It's a little trickier here. This represents A and not B, which is the complement of B. C represents complement, everything that's outside of B. What's shaded here includes everything, it's things that are in A, but also things that are outside of B. This is the opposite. This is B and the complement of A. And this is what they have in common, A and B. Both occur when you are in that region. These are problem-solving tools. We're thinking of these in terms of sets. These are sample spaces and events can be thought of in terms of sets. And it's a nice way to visualize it. It's going to have more meaning when we look at an example. Let's look at an example. Well, here they can get complicated. I'll come back to that. Here's an example. Jennifer has applied to graduate school at both Harvard and Caltech. She thinks her probability that she'll get into Harvard is 0.4, and the probability she'll get into Caltech is 0.6, and the probability that both will admit her is 0.25. This is her assessment of the probabilities, okay? She very well could be wrong in her assessment. So this is more of an informal assessment. It's not based on any formulas with these probabilities. It's just her guesses. Based on these guesses for these probabilities, we can answer a couple questions. A, what is the probability that neither university admits Jennifer? B, what is the probability that she's admitted to Caltech but not to Harvard? A Venn diagram can help us solve this. It's a problem-solving tool. Instead of labeling them with A and B, it would make more sense to label them with, say, H and C, or H and CT. I'll do H and C. H for Harvard and C for Caltech. You don't have to do this, but I think it's a good idea to help your intuition to draw these circles with an area that's approximately the fraction of the area represented by these probabilities. Now it's hard to get this perfect. I mean, nobody can really get it perfect. But try approximately. So for Harvard, it's a little smaller circle than for Caltech. Let's draw Caltech's first. Pretty big circle or blob there. That represents getting into Caltech. Label it with a C. A little smaller circle or blob for Harvard. And yeah, it's not a perfect drawing by any means. I'm pretending in my mind that the area of this blob for C represents 60% of the entire area for the box. I don't think it's quite that big. And I'm pretending that the area for H represents 40% of the area of the entire box, because those are the probabilities. Being in the intersection here, where they both occur, that would be probability 0.25. This set is H and C. That's where she gets admitted to both Harvard and Caltech. Go ahead and label that with the probability of 0.25. And that's definitely not a quarter of the entire area. So again, my drawing's far from perfect. But you can try to make it better if you wanted to. Okay, that's what you should start labeling with. We're going to continue labeling to help us try to answer these questions. For example, in question A, it asks, what is the probability that neither university admits her? That means she's in neither of these circles. She's outside of both of them. Okay? You can even imagine this is a gym. Okay? This is a floor of a gym, and you've got these big circles representing what happens as far as her admittance. If neither university admits her, she should not stand in either circle. She should stand outside of them. So we can represent, hopefully, the answer based on the number we label outside of both the circles. Part B asks, what is the probability that she's admitted to Caltech but not to Harvard? So she'd be standing in the Caltech circle but not the Harvard circle. We'd want to label this region, this crescent moon type of region, with a number representing that probability. But how? Should I label, based on these numbers, should I label this with a 0.4 and this with a 0.6? Do you think that's a good idea? It's actually not a good idea. I think I heard some no's. The no's have it. It's a good idea to label each region with a probability for just that region. And this 0.4 represents everything that's in H, which is the 0.25 plus whatever's in here, in this crescent shape. That's in H but not in C. By the addition rule, for disjoint events, I mean, these two regions are disjoint. They are separate from each other. There's no overlap. The probability of being in one or the other region is the sum of the probabilities, and that sum has to be 0.4. Therefore, the number that's got to go here is 0.15, because 0.15 plus 0.25 is 0.4. That went by fast. Should I say it again? I start by labeling the 0.25 with the common intersection, because that's the probability of being admitted to both. I would like to label this crescent moon shape with the probability that she's admitted to Harvard but not to Caltech, because it's in the Harvard circle but not the Caltech circle. I know her total probability of being admitted to Harvard is 0.4. These two probabilities have to add up to 0.4 because of the addition rule for disjoint events. The entire circle is like 0.4, 40% of the area. This is 25%. I've got to figure out what number to go there so that these two things add to 0.4. 0.15 is the answer. 0.4 minus 0.25 is 0.15. Likewise, look at Caltech. Her total probability of being in the C circle is 0.6. I want the numbers that these get labeled with to add to 0.6. So this has got to be 0.6 minus 0.25, which is 0.35. Those are all disjoint events. Being outside of both circles is also disjoint from those events. And all four of these disjoint events have to have probabilities that add to 1. What do these add to? 0.15 plus 0.25 is 0.4, plus 0.35 is 0.75, 1 minus 0.75 or 0.25 is what's got to go outside of both circles. And that's the answer to part A. The probability that neither universal answer. Part A, the answer is 0.25, and your work essentially at the moment is this picture. There will be formulas we'll look at in a few minutes, but for the moment your work is to look at the picture. You realize these have to add up to 1. Part B says what is the probability that she's admitted to Caltech but not to Harvard? So she's in the C circle but not the H circle. We already wrote the answer, 0.35. Okay, so Venn diagrams like this, if you think about them correctly, as I described, are real nice problem-solving tools. They allow you to solve problems like this actually without formulas by just thinking about them, although we really are using the addition rule for disjoint events to think about that. We're going to come back to this example later, but here are some formulas that are useful, and we could think about that previous problem with the following formula, something called the general addition rule. Says if you want to find the probability of one or the other thing happening, whether A and B are disjoint or not, add up their individual probabilities and then subtract the probability that they both occur. Sometimes you'll also see this written with union and intersection notation. If you know what that is, great. If you don't know it, don't worry about it. I'm just making a remark for the record. Union represents or. It's this symbol that kind of looks like a U. Union starts with U. Intersection is this symbol. It's kind of like, acts like the word and. It almost looks like an A, except you don't put a horizontal line. If you've seen that notation before, great. If you've never seen it, don't worry about it. We're not going to use it. It's in here for the record. Mostly focus on the first one. This formula can be intuitively thought about in terms of the Venn diagram again. Here's A, here's B. Draw with some overlap. What's the chance that event A or event B occurs, or both? It's not an either or, it's one or the other or both. For one or the other or both to occur means you are in one of these circles or possibly in the overlap. If you imagine these probabilities as representing the areas of A and B, essentially you're saying to find the total area of what I shaded here, take the area of A plus the area of B and subtract off the area of what they have in common so you don't double count it. This rule always works. It's always true, no matter whether A and B are disjoint or not. If A and B, by the way, are disjoint, they have no overlap. I draw the Venn diagram without any overlap. This rule is still true because the intersection is empty. They don't have anything in common, so the probability that they both occur is 0. So the rule still holds for disjoint events. It's just that the last term that you subtract is 0. Again, if you think intuitively in terms of these probabilities as being areas, you don't have to think of it that way. But if you want to, if it's helpful, this would say the area of A or B, meaning one or the other or combined, what I've shaded here is the area of A plus the area of B minus the area of what they have in common. Again, the subtraction would occur so you don't double count it. And again, I'm thinking of it in terms of areas just because it's a nice way to think about it. You don't have to think of it that way. In terms of the last problem that we just did, this one here, the probability that she's admitted to Harvard or Caltech could be figured out with the formula that I just showed you on the other slide, this general addition rule. It's the probability that she's admitted to Harvard plus the probability that she's admitted to Caltech minus the probability that she's admitted to both. And this information is in what we're given. The probability of being admitted to Harvard was 0.4. The probability of being admitted to Caltech was 0.6. The probability that she's admitted to both is 0.25. This calculation, 0.75, represented the area of both circles put together when you include the overlap. The area outside of it, the probability outside of it, was 0.25. That was the answer to part B. Excuse me, part A. 0.25 was the answer to part A. Was it the answer to the other one too? Were they both 0.25?
No, part B was 0.35.
0.35 for part B. Okay, 0.25, 1 minus that was the answer to part A. This is the probability that she's admitted to one or the other or both. What's the probability that she's admitted to neither? 1 minus that. 0.25 was the answer to part A. So you also can solve that with the formula, but I think the Venn diagram approach, for simple situations at least, is simpler than the formula approach, though you should be comfortable with both. We're going to think more about cards here next. We need to continue thinking about conditional probabilities. And we're running low on time, it's almost quiz time. This was our example from last time. Let me just end for the quiz with these formulas here. And then we'll try to explain the formulas a little bit after the quiz. These are formulas for conditional probabilities. We talked about conditional probabilities last time. This notation is strange. Yes, it is strange, but what does it mean? It means the probability that B occurs if it is known or given that A has occurred. The vertical line you should think of as a shorthand for given that or is known that. You could switch around the roles of A and B. They're just symbols anyway. You can think about the probability that A occurs if it is given that B has occurred. These are the formulas written both in terms of and in terms of intersection. You can just focus on these forms. We'll just get it down for the record here before the quiz. We'll talk about why these formulas make sense after the quiz. Let's get ready for the quiz right now.